Sometimes a paper comes along that doesn't just ask you to think, it demands it. It grabs you by the shoulders and says, everything you thought you knew, maybe it's not the whole story. Reading New Interpretation of Relativity by William D. Walker is a direct challenge to your understanding. This isn't light reading. It's a deep dive into the universe's fabric. Walker is an author who steps outside conventional thinking. He's proposed ideas that could turn modern physics on its head. He's not just tweaking the equation, he's suggesting a fundamental rethink of how we understand space, time, and gravity itself. Walker works outside traditional academia as an independent researcher. His paper is the culmination of that independent work, a challenge to the established order, a new voice after a century of the same ideas. The piece is dense and packed with thought-provoking arguments. Walker builds his case piece by piece, starting with the foundations of Einstein's work. Then he systematically proposes his own alternatives. He questions assumptions physicists have taken for granted for decades. Before we can understand what William D. Walker is proposing, we need to get a handle on the ideas he's challenging. Einstein's theories of relativity, special and general, are the bedrock of modern physics. Special relativity, which he published in 1905, introduced some mind-bending concepts. The big one is that the speed of light in a vacuum is constant for all observers, no matter how fast they are moving. This simple idea has huge consequences. It means that space and time are not absolute. Space and time change depending on how fast you move. They are not fixed. This leads to some famous effects like time dilation and length contraction. Time dilation essentially means when a clock is moving at high speeds, it actually ticks slower than if it wasn't moving at all. Time passes more slowly for moving objects. It's not just a mechanical error. Length contraction means that an object moving at high speed will appear shorter in the direction of its motion. Einstein showed us that space and time are woven together into a single fabric called space-time, a four-dimensional stage where all events in the universe unfold. 10 years later, Einstein gave us general relativity. This was his theory of gravity. Isaac Newton had described gravity as a mysterious force pulling objects toward each other. Einstein had a completely different idea. He said there is no force of gravity. Instead, massive objects like planets and stars warp or curve the fabric of space-time around them. Smaller objects like a satellite or even a beam of light simply follow these curves. So, the Earth isn't being pulled by the sun. It's following a straight path through the curved space-time created by the sun's immense mass. It's like rolling a marble around the edge of a bowling ball placed on a trampoline. This theory has also been confirmed with stunning accuracy. It predicted that light from distant stars would bend as it passed by the sun, which was observed during a solar eclipse in 1919. It explains the strange orbit of Mercury, which Newton's laws couldn't quite account for. And it's the reason our GPS systems work. Satellites in orbit experience time differently than we do on the ground. Our GPS systems work only because we correct for this difference, a direct result of general relativity. These theories have become the foundation upon which we've built our understanding of black holes, the Big Bang Theory, and the expansion of the universe. Now, enter William D. Walker and his paper, New Interpretation of Relativity. Walker studies Einstein's established structure and suggests the foundation might be flawed. His central argument is a radical departure from a century of scientific thought. He argues the speed of light is not the ultimate cosmic speed limit. Instead, the true constant is the speed of gravity. Gravitational signals might propagate far faster than light, possibly even instantaneously. This claim attacks the first pillar of Einstein's special relativity. Walker introduces a new model for how the universe works. He argues time is not relative as Einstein described. Rather than time stretching and shrinking, Walker says the properties of matter change with velocity. He reinterprets time dilation, not time itself slowing, but the operational rate of physical and biological processes slowing at high speeds. A clock in a speeding spaceship ticks slower because its internal mechanisms are affected by motion through a proposed gravitational medium, not because the flow of time changed. Walker re-examines space-time. Einstein unified space and time into a flexible fabric. Walker seeks to decouple them. Space is a three-dimensional arena. Time is a separate, universal measure. Gravity is not curvature of space-time, but interactions within a universal medium filling space. It feels classical in form, but enforces a new set of interaction rules. Walker's blueprint aims to resolve lingering mysteries in physics, the nature of dark matter and dark energy. To truly grasp the weight of Walker's arguments, it helps to look at the specific examples he uses to challenge accepted physics. One of the key arguments he presents, paraphrased from his piece, is that the results of experiments confirming time dilation, the Haffel-Keating experiment with atomic clocks on airplanes, are misinterpreted. The clocks did not experience a slowing of time itself. Rather, their atomic components experienced increased kinetic resistance from a background gravitational field, causing them to oscillate at a slower rate. This is a direct assault on the conventional interpretation. Another powerful point Walker makes concerns the phenomenon of gravitational lensing, where light from a distant galaxy is bent by the gravity of a massive object in front of it. Mainstream physics explains this perfectly using Einstein's theory of curved spacetime. However, Walker argues that his model can also explain it, but in a different way. He writes something to the effect of, the bending of light is not due to spacetime curvature, but to a change in the refractive index of the gravitational medium surrounding a massive body. Just as light bends when it passes from air to water, it bends as it passes through the denser medium near a star or galaxy. Walker also tackles the famous equation E equals mc squared. He doesn't dispute its validity, but reinterprets its meaning. Walker suggests that the equation is more of a conversion factor within his proposed system. Energy is how much something moves. Mass is how much it resists changing that motion in gravity. The differences between Walker's ideas and Einstein's are not just small details. They represent a fundamental clash of worldviews. The most significant point of departure is the speed of light. For Einstein, the constancy of the speed of light is non-negotiable. It is the absolute law upon which his entire theory of special relativity is built. It's the reason time and space must be relative, but Walker throws this cornerstone away. He suggests that the speed of light can vary. It is the speed of gravity that is the true, unchanging constant. This single change creates a domino effect, requiring a complete reconstruction of physics as we know it. This leads to a second major difference, the nature of time. In Einstein's universe, there is no universal now. Two observers, moving relative to each other, will experience time differently, and both of their perspectives are equally valid. This is the core of relativity. Walker's theory, on the other hand, seems to reintroduce the idea of a universal or absolute time. By claiming that changes in clocks are due to physical effects rather than the nature of time itself, he implies there is a master clock for the universe ticking away at the same rate for everyone, everywhere. This brings back a more intuitive Newtonian concept of time that Einstein's work had seemingly disproven. Their views on gravity are also worlds apart. Einstein's general relativity describes gravity as a geometric property of space-time. When a book like New Interpretation of Relativity makes such audacious claims, the reaction from the scientific community is often swift and skeptical. Mainstream physicists, who have spent their careers within Einstein's framework, are naturally resistant to ideas that seek to tear it all down. The overwhelming consensus is that Walker's theories, while intriguing, lack a rigorous mathematical foundation and, more importantly, the experimental evidence required to be taken seriously. They point out that Einstein's theories have been tested and verified for over a century. The bending of starlight and the detection of gravitational waves by LIGO. Critics often highlight that Walker's ideas are not presented in the language of modern physics. Scientific theories today are expressed through complex mathematical formalisms, like tensor calculus for general relativity. Walker's book, while detailed, is often described as being more conceptual and philosophical, lacking the precise mathematical models that would allow for testable predictions. It's one thing to have an idea, but it's another thing entirely to formulate it into a mathematical theory that makes new, unique predictions that can then be tested against observation. Walker has not yet crossed that bridge. Furthermore, many of Walker's proposals, such as the existence of a universal medium, or ether, are seen as a step backward. The concept of an ether was largely abandoned after the famous Michelson-Morley experiment in 1887 failed to detect it. While Walker proposes a new kind of medium, his critics argue that he doesn't provide a compelling reason to resurrect the idea or any new evidence for its existence. The scientific community generally operates on the principle of Occam's razor. The simplest explanation that fits the data is usually the best. However, it's not all outright dismissal. In some corners of the internet and among amateur physics enthusiasts, Walker's book has found a receptive audience. They see him as a modern-day Galileo, fighting against a rigid establishment. While this grassroots support is significant, it has not translated into acceptance within academic circles. The bottom line is Walker's theory challenges Einstein, sparking debate and pushing science forward. Progress is impossible without someone daring to ask, what if we're wrong? No matter the outcome, questioning our understanding is what drives discovery.